So I'm happy to introduce our first speaker, Gianira Alfarano, to tell us about the direct sum of q-matroids and linear sets. Please.
Thank you very much. Can you hear me? It's okay? Good. So thank you, first of all, to the organizer for giving me this opportunity. I thought I would have been the first one speaking about q-matroids. That's not the case, but that will be a good repetition. And my background is coding theory, actually, algebraic coding theory, and that's why I'm interested in a representability question for matrices and q-matrices, because when you talk about representability, you essentially talk about codes. And indeed, my talk will be about the representability of the direct sum of q-matrices and some geometric tools that we can use to look at this question, in particular linear set. I know that most of you are not familiar with these things, but I'll try to be slow and less technical as possible. Okay, so this is the basic notion of a matroid given with the rank axiom. Keep this just for fixing my notation. So a matroid is a pair where the first entry is a finite set, 1 to n, and R is the rank function. The rank function takes as input a set and gives an integer value which satisfies this tree property, okay? So the rank is bounded by above by the size, is non-decreasing, and satisfies the submodularity. K will be always the rank of the matroid, and the matroid has a height n, which is the size of the finite set, the ground set. Okay, and now it starts with a different notion of representability. It's completely equivalent to what we know, but I prefer to use this one. And it comes to finite geometry, my background in finite geometry here. So I take a multi-set of points. Multi-set means I can repeat them, possibly, in the projective space of dimension k minus 1 over some field, usually finite, but not necessarily. These things is known as a projective system if we do not allow this point to belong to the same hyperplane. Okay, and now I define a function that takes a subset of 1 to n as input and gives me this value, which is 1 plus the dimension of the span of the points indexed by this set. Okay, so this is just the projective version of the columns of the matrix that you see usually for representability. And this rank function satisfies the three axioms, and so it is indeed a rank function, and we call a matroid that has such a rank function can be written in this way, a representable matroid. Since I want to get rid of this n here, I can just write to the p, and the matroid I will consider as ground set for the matroid just the multi-set of points. This is completely equivalent to the classical notion of representability. There is a +1 because I work in the projective space, so, but it's equivalent. This is convenient for me to make the Q analog. Okay, so so far so good. We are happy with this. Okay. Now I can make the Q analog. So when you make a Q analog of things, you usually take, if you have a finite set, you will consider a finite dimensional vector space. And my finite dimensional vector space will be fq to the n, so the n-dimensional vector space over the finite field fq. And I will define a function. This time, it takes as an input a subspace of fq to the n. So this L denotes the lattice of subspaces of fq to the n, and gives me an integer. And this function satisfies this three axiom, is upper bounded by the dimension of the space now. It's non-decreasing, and it obeys the submodularity. But note that now the operation are the vector space sum and the vector space intersection. Okay? So K is still the rank of the Q matroid now, so is the row of the whole space, and the height of the Q matroid is n. So I can define a Q matrix as this pair of Q to the n and this rank function. So this is as it has been defined in 2018. We already heard yesterday that the traces of Q matroids already appears in a Crepo PhD thesis, so are much earlier than 2018. And so the question is, what is the Q analog of the representability? And since matroid generalized the notion of linear independence of columns of vectors over some field, what does q-matroid generalize? So the first question has been answered already in the paper, because q-matroid actually have been introduced for this reason, and representability has been given via rank metric codes. I will change a little bit this notation, but in an equivalent one. And we will see the second one, the answer to the second one. So what q-matroid generalize? Okay, so to do that, together with Imer Byrne, we try to understand the geometry behind the representability. So in geometry and rank metric codes, we often use this object. We call it a Q system, which is actually the geometric counterpart of a rank metric code. But this is nothing but an n-dimensional FQ subspace of FQM to the K. So FQ to the M is an extension field of FQ, and I define a Q system to be an n-dimensional FQ subspace of FQM to the K. This is important. And this is just a technical thing that I need to impose to not have weird things happening. So I assume that the span over FQ to the M of this space is the whole space. Okay, and now note that this is an n-dimensional FQ subspace, so it's isomorphic to FQ to the N. So I can actually define a Q-matroid where the ground space is this system. And that's what I do. I define this function that takes a subspace of S and gives me the dimension over FQ to the M of the FQM span of this space. My claim is that this is the Q analog of the representability I gave you before. I will not show this, but it is. And we say that a matroid, a Q-matroid that can be written like this as an S and with such a rank function is FQM representable. So when you talk about representability in matroids, you need to find a field where the matroid is representable. Here the field is fixed by FQ. Okay, this is an FQ space. I need to find an extension field. I need to find M, the extension field, where I can represent the Q-matroid. I need to find this little m here. Okay, and why I do this is just to support my statement, because if I look at this now, the independent spaces are those spaces whose rank is equal to their dimension. But this means that the dimension over FQ of these spaces is equal to the dimension over FQ to the M, or their FQM span, and these are called the subgeometries of the system. And the bases are the canonical subgeometry of the system. So those are objects that already exist. So I'm trying to bridge things that already exist with the concept of Q-matroid. Okay. If we are happy with this, so in the past years, a lot of work has been done to find all the cryptomorphic equivalent definition, a cryptomorphic definition of a Q-matroid. We succeeded in terms of all these things. And let me highlight that these are non-trivial Q analogs, in the sense that since we are working with vector spaces, the difference is that when you take the union of sets, the union is nice. But when you take the sum of vector spaces, the sum is not nice anymore. So a lot of things can happen. And so these are non-trivial in the proofs. So I will be interested just in independent spaces and in the cyclic flat. So the independent spaces are the spaces whose rank is equal to their dimension. And the cyclic flat are the spaces which are flats. So whenever you have a one-dimensional space that is not already in the space, the rank must increase. And they are also open spaces. Whenever you take an hyperplane, a codimension 1 subspace, the rank stays the same. So you go up, the rank increases. You go down, you take codimension 1 subspaces, the rank stays the same. So I will just use these two things, independent spaces and cyclic flat, and these are related by the following theorem. So if I have a Q-matroid with a rank function rho, I is independent in the q-matroid if and only if the dimension of I intersection every cyclic flat is at most the rank of the cyclic flat. So given the cyclic flat with their rank, I can identify the independent spaces. So now I'm interested in a special family of q-matrices, which is the uniform one. We have seen the uniform matroid these days, and this is the counterpart, the q-analog, the uniform q-matroid. You can define essentially in a similar way. We fix k between 0 and n. Can be 0 and n. I just will exclude this case to allow a unified treatment of everything. It can be also 0 or n. And I define, the rank function as the function that takes a space and associates the minimum between k and the dimension of the space. For the uniform matroid, you just take the size of the space. So this is the q-analog. And I call this q-matroid ukn is a uniform q-matroid with the rank k over fq to the n. I like this q-matroid because a lot of things are known. First of all, we know that is fqm representable if and only if m is larger than n. This comes from coding theory. Also, if a Q system represents ukn, this Q system is called k-1 scattered. I'm not defining what it is, but it's something that is really well studied, well understood in finite geometry. Scattered spaces are used all the time. And in particular, this relates to the existence of maximum rank distance codes. And finally, more important for my purpose is that a q-matroid is uniform if and only if its lattice of cyclic flat is given just by the 0 space and the whole space, and the ranks are 0 and k. Okay, so it's characterized by the lattice of cyclic flats. So here I can go fast because all of you know the direct sum of matroids. So you have two matroids over two ground set, and you make a new matrix over the disjoint union of the two sets. And by taking the rank is just the sum of the two ranks. What is nice in the matroid, classical matroid, is that the structure that you have come from, for example, the independent sets are the disjoint union of the independent sets of the two summands. Same for the bases, same for the flats, and so on. And also, we have a nice representation. I will skip this because it's I just use my geometric notation. I will skip this. If you think about matrices, we have a diagonal block matrix where the blocks in the diagonals are the representation of the two summands. This is equivalent. But when you go to the direct sum of q-matroids, you lose all the similarity between a matrix and q-matroids. So the direct sum really shows you that these two things are quite different from each other. And so let's try to make the direct sum. This has been defined by Cherry and Urius in 2022. And we start with the two q-matroid over ground spaces of dimension n1 and n2 respectively. And I want to construct a new q-matroid over the direct sum of the two spaces. So I denote by pi I the canonical projection onto the first n1 and last n2 coordinates. And now I define the rank function in this way. Okay, pretty ugly way, but it satisfies the rank axioms. So this is a q-matroid, and we call this the direct sum of m1 and m2. Okay. The problem is that now we cannot describe any more independent spaces, flats, bases with the direct sum of the independent spaces, flats, and bases of the two summands. So this doesn't work anymore. And why is this? Because a union is not a sum. And in particular, you cannot write all the subspaces of fq to the n as the direct sum of a subspace in fq to the n1 and fq to the n2. So you don't have this sum of the ranks in general. So this is the problem. And that's why that minimum in the rank expression is important. Okay, so this is the direct sum, and now the question is when the direct sum is representable. Well, this question has been asked recently by Glusing, Lursen, and Jeni, and they established three main things. The first thing is this one. It says that if the direct sum of two q-matroids is FQM representable, then the two summands are FQM representable, so are representable over the same field. And the representation is given by the direct sum of the two systems. Okay, we are happy with this, so it's not different from the matroid case. But now, this is the interesting thing, the direct sum of representable q-matroids is not always representable. We have examples of a direct sum of two q-matroids that is never representable over any field. And this is an interesting, it's an example, but it's an interesting example. And finally, they look at U12, so uniform q-matroid of rank 1 of height 2. They sum it with itself, and they show that is FQ to the M representable if and only if M is larger than 4. So this means that we can have three things. The direct sum is always representable, is never representable, is representable over a sufficiently large field. And to establish these things, the main idea they used is that the cyclic flats behave well, are the only thing that behave well, in the sense that the cyclic flat of the direct sum is the direct sum of the cyclic flats of the two summands. And this is the only structure, really, the only one that behaves well. Okay, so what do we do with this? Well, we, I did not say, but this is a joint work with Relinda Iurius, Alessandro Neri, and Ferdinando Zullo. We took their example, U12, U12, and we try to generalize this. We look at the direct sum of two uniform q-matroids, the general q-matroids. Why? Because we know the cyclic flats, we know all the properties that I showed you before. They are representable, the system is a scattered space. Okay, and now this is the technical part. So interrupt me if you want to know more. So I fix K to be K1 plus K2, just the sum of the two ranks. And I define this set. This set here is the set of all FQM hyperplanes of FQM to the K, so K minus one dimensional subspaces, FQM subspaces, that do not contain these two spaces here. Okay? I call this set lambda. And now I use a notion that was already there in the literature, a notion of evasiveness. I call a system lambda H evasive if the dimension over FQ of the system intersection any space in this lambda is at most H. This is an intersection property, a little bit technical maybe. But what's nice is that we can prove the following equivalent statements. We have that this system is an FQ representation of the direct sum, if and only if this condition holds, and this is nothing but imposing that the cyclic flats are just the direct sum of the two cyclic flats. So we have only 4 cyclic flats in the direct sum, the 0 space, FQ to the n1 plus 0, 0 plus FQ to the n2, and the whole space. And so we get this dimension condition. So we have I's independent if and only if these three things hold simultaneously. And finally, this is the most interesting thing, we have that the system is evasive. It's a characterization. So if we are able to find an evasive system, we are done. We show that the direct sum is representable. And that's indeed the case. So whatever K1 and 1, K2 and 2 are, we have that the direct sum of two uniform q-matroids is always representable somewhere. So over some FQ to the M. Okay, and the construction, we exhibit the construction, works like this. So assume first that N1 and N2 are coprime and take M, so the extension that we need to be the product N1 and 2. And now we take as a representation of the uniform q-matroid these two spaces. Those are the two well, in my notation, those are Ni, Ki spaces, Q system, Ni, Ki, Q system. So Ni dimensional subspaces in FQM to the Ki. Believe me if you don't see this immediately, but these are FQ spaces. And it's not extremely difficult to show that the direct sum of these two spaces is evasive. Okay, so if N1 and N2 are not coprime, you can work a little bit, but you can apply essentially the same construction over a larger field. So essentially, this says that if M is sufficiently large, then we can represent the direct sum of two uniform Q-matroids. This can be generalized to the direct sum of T uniform Q-matroid. You just take more SIs and M to be the product of N1, N2, and T, and so on. Okay, so now questions. We showed that the direct sum is representable somewhere, but can we characterize the extension fields where it is representable? And if we cannot solve this question, can we say what is the minimum M? Because we don't want to go over a super large field. Can we say what is the smallest M that we need? Well, the answer is in generally not. But if we look at the special case of the direct sum of Q-matroids rank 1, we have that this is equivalent, really, it's a one-to-one correspondence. It's equivalent to linear set on the projective line, some special linear set, which are some special geometric structure that are called with the complementary weights. And these particular linear set were studied by Napolitano, Polverino, Sant'Anastasio, e Zullo. And thanks to this, we can apply the result on the existence of linear set with a complementary weight to answer these two questions. And so the answer to the first question, so the red part essentially is what is contained in this paper. Sorry, the black part is what is contained in this paper. The red part is our new condition. So we have that if at least one of these things hold for M, then M is a valid field extension where we can represent the direct sum. And the minimum such M for the direct sum of Q-matroids of rank 1 is 2 times the maximum N1 and N2. So we don't need N1 times N2. We just need this. And with this, I thank you for your attention. If you are interested, the preprint is there. Thank you.
Questions? Oops, there we go. Questions?
Just question about the q-matrix. Do we have Todd polynomial for the q-matroid?
Do we have, sorry?
Todd polynomial?
Yeah, Andrew worked on the Tat polynomial for Q polymatroids, so it's a bit different. So you did for Q polymatroids, right? I guess. Q polymatroids, no? You worked out? Q matroids, okay. Yeah, so it's a bit more complicated, but we do have a version of it. Yeah. Yes.
Why is this the right stuff? Why is something else?
Why we...
Why is this operation, why is the right sum the right thing?
Okay, so, well, so I don't know if this is a good answer for this, but Glusel, Lersen, and Jani showed that this is the only coproduct in the category of Q-matroids where the morphisms are weak maps. So, and it's the most independent Q-matroid among the category of matroids where the restriction to first space and second space are the original Q-matroid. So this is the right notion, essentially. I don't know if this answers. Okay, thank you.
Do you think there's a hope to characterize when it is representable?
In general or for uniform?
In general.
Well, yes. If you know the cyclic flats. So essentially, this says that you need evasive property with respect to the cyclic flat. You need that the system evades the cyclic flats somehow. Okay? So if you know in principle the cyclic flat, you can write down an equation like this. Here it's easy because we only have 4 cyclic flats and 1 is the 0 space, so it doesn't give you any real information. But you will have as many equations as the number of cyclic flats in this. So if in principle you know the cyclic flat and you can develop some evasive property, I think you can. But in general, if you don't know the cyclic flats, I don't know if but geometrically speaking, I think this is the right way to look at the problem.
All right, let's thank Gianira again.
Thank you very much.